Hello and welcome to our talk, Page Cache Attacks, Microarchitectural Attacks on Flawless Hardware. This is a talk with Trishita, Tiwari, Schwarz, and Erik Kraft, and me, Daniel Gruss. So let's start right away. So we want to talk about the microarchitecture today. Microarchitectural components are components of the processor which are not defined in the architecture, but they still exist and they still are different and behave differently depending on the processor. So you can have, for instance, different caches, buffers in different CPUs. You can have predictors, and all of these microarchitectural elements, they have a behavior that you can observe, but they are not documented, or at least their exact behavior is not documented in the architecture specification. So this is meant to be transparent for the programmer, but the timing optimizations, for instance, they will then lead to sidechannel leakage.
That all sounds a bit abstract, right? Maybe we should go into some example, like a CPU cache, something that many people will already know. So if I take a CPU cache, for example, like here in the middle, and I have a short code snippet on the left that accesses one variable twice in a row. So at first time I do that, this variable is not cached. So I've never used that before, and it has to be somewhere in the DRAM. So this request has to go to the DRAM, in the main memory, and search for this variable.
This sounds very slow.
Yes, that sounds slow. I have to wait for the response of the memory, and then it will be, as you said before, put into the cache transparently. And the next time I use this variable, and it's already in the cache because I've recently used it, then I can take it directly, this copy from the cache, and use that one. And as you said, going to the main memory, this is really slow. But if it's in the cache, then it's much, much faster, and we can really measure that.
This is really great. So if we get much faster CPUs just by adding a cache, then we can save a lot of time and energy. So let's take a look at the histogram here. If you look at this histogram, this is a log scale histogram, right? And you can see that virtually all the accesses are here around, in this case, below 80 CPU cycles. And you can see that virtually all the accesses are here. So this is a lot of time that we can save here, because if you compare this with the cache misses, they are all very, very slow. So you can see the timing here is always above these maybe 200 cycles.
See, that's what I told you. It's much faster if something is in the cache. And you can really see that when measuring the access times.
This sounds like a really cool thing, but why would that be relevant for our talk about page cache attacks?
It turns out you can build attacks with that. With this simple timing difference, you can already attack some applications. Let's see, for example, in this setup here, we have an attacker application, we have a victim application, and we have some shared memory, and of course, this transparent cache that we have in every CPU. Now, if the attacker or the victim access the shared memory, it doesn't matter who does it, it ends up being in the cache. Transparently, no one does anything actively there, it just ends up there. Now, if the attacker flushes something from the cache, so removes it from the cache, removes this copy, then it's also gone for both an attacker and a victim application. So an attacker can do that and then wait for the victim. And the victim now might access some shared data. Again, the shared data might be some library like the libc, or some keystroke library that handles keys, or whatever, some shared library, some shared memory.
But this doesn't really sound very dangerous, right?
Yes, but think about that. So when the victim accesses that, it's again in the cache, the shared memory, and now the attacker can also access it, it's shared. So the attacker can see whether it's in the cache or not by measuring the access time. So then the attacker learns whether the victim accessed some data or did not access some data. So that's some information that you might not want to share with any other application if you are an application.
So this sounds like a very simple attack, but in many cases, the attacker will not have shared memory with the victim, right?
That's true.
What can we do then?
So it turns out this is not the only attack. There's a different attack that's quite similar. It also uses the cache, it also uses its timing differences, but does not rely on shared memory. So in this case, the attacker simply fills the cache with its own data and then waits. If the victim now accesses some data that falls into the same cache set, then there is no space, no empty space for that, and some data of the attacker has to be evicted. It's not in the cache anymore, but replaced by the victim's data.
Okay.
Now, if the attacker, again, fills the cache with its data, the data that's already in there, that will be fast, it's a cache hit. But if it was replaced, it has to fetch that from the main memory again, put it into the cache, and this will be slow. So in overall, we see a bit of a slowdown when doing that.
So it's a similar attack to the previous one, and you don't need shared memory. So this is really nice. But
yes.
Can you actually leak information with that? I mean, there are not that many cache sets, and there will be tons of noise in a system, right?
So maybe we'll start with an easier example. Didn't you do something with flush and reload and keys recently?
Oh yeah, I think we did something there, but I have a very, very bad memory. Let's take a look at maybe this plot here. So here we perform flush and reload on keystrokes, and we just measured when the library has some activity, and whenever it has some activity, we printed this, and we plotted this in this graph here. And you can see clearly the ground truth is illustrated here with the green dots. You can clearly see that you can see the keystrokes in this trace just based on the sidechannel attack. So this is flush and reload, and it does not really reveal the actual key, but it has a timing difference between the keystrokes here. And this you can use to actually leak data, for instance, by using machine learning and learning what the inter-keystroke timings are.
Okay, but hopefully my password is not in a dictionary, not a word, a normal word.
But still you will have distinct movements. If you think about the keyboard, you have movements from one letter to the other. So there will be distinct movements from one letter to the other that have different timing. And based on that, you will be able to infer some of the keys.
Okay, I can believe that. But do we also have some stronger attacks?
I think we have some stronger attacks, and if I recall it correctly, you even published some of those, and you're even going to give another Black Hat Asia talk about one of these.
Oh yes, true. Now I remember.
So
yes.
One of them was Meltdown, for instance, but we also had Foreshadow, we had Zombie Load.
Zombie Load, right?
Yes, Zombie Load.
That's what I'm talking about in this talk.
No, you're not in the Zombie Load talk here. Michael,
No.
No, this is not the Zombie Load talk.
Yeah, right. Thanks for reminding me.
Okay, and Spectre. We also have Spectre. I mean, Spectre is also a very interesting attack. But we don't have time to go into details of these all. And also, we wanted to talk more about the page cache attacks, right?
Yes, we just wanted to have some examples here on what you can do with these small timing differences in a microarchitecture.
Mm-hmm. So let's talk a bit about countermeasures for these attacks, because this is also an interesting property, because these are attacks that we mount from software that exploit a problem in the hardware and then leak the data again to the software-based attacker. So this crosses the layers somehow, and this makes it difficult to mitigate these attacks properly.
Can we even do that?
It depends. So for processors that are already shipped, you can't really fix them, right? I mean, I can hand you a soldering iron, but good luck with that. And of course, you can work around the problem. For instance, we did that with the Kaiser patch, which is now in Linux as KPTI, but also the other operating systems all adopted this. And this just adds more software level isolation and makes exploitation harder, but it doesn't fundamentally solve or fix the problem. It only works around the problem. Yeah, and then it's very difficult to fix these. For instance, for caches, we talked about the cache timing attacks, right?
Yeah, you don't want to fix that.
Yes. because we want the performance there. So it's not very easy to fix that.
No one wants to give up caches.
Yes. For Spectre, it would be predictions. You don't want to give up predictions on what to do next. So we are only fixing the symptoms. And that's, of course, not very good. And we have to get better at that. But maybe in a few years, we will know how to fix these problems more fundamentally.
Yes, that sounds like we would need a new design for that.
Yeah, maybe we will need that. Yes.
But what if we assume that we are in a parallel universe?
Okay.
And hardware is not that complex and hardware is fine.
Okay.
What about softwares and side channels? So we don't have any hardware side channels now. Everything is fixed. We're in a parallel universe. We're in the future. We had the greatest minds coming up with hardware designs that are not vulnerable anymore.
That would be great. I mean, then we would be all fine because the problem would not exist anymore, right?
I think so.
Perfect. Okay, so this is great. And with that, we are at the end of our talk, right?
Thanks for your attention.
Wait. We have so much more to talk about. What about the software side channels that we just discussed?
But the microarchitecture doesn't exist on the software level, right? This is the hardware thing.
Well, but there are parallels between the hardware and the software. For example, if you see, there's the ISA extensions and the parallel in the operating system is non-standard system calls. Similarly, hardware caches have software caches as their parallel, and the hardware prefetcher has the software prefetcher.
So that would mean hardware and software is basically the same with respect to sidechannel attacks?
Maybe. So maybe what we could do is like apply some of the principles from hardware side channels to software attacks. And now we can discuss our hardware agnostic side channel through the operating system page cache. So this side channel has a temporal resolution of about 2 microseconds, which leads to up to 6.7 measurements per second on Linux and 466 nanoseconds, which is about 233 measurements per second on Windows. And a spatial resolution, since it's a page cache attack, it's 1 page, which is 4 kilobytes. And we can do very, very different types of attacks through this. So PHP random number generator attacks, UI redressing attacks, breaking ASLR, keystroke timing attacks, you name it. Covert channels, we have it all.
So now let's talk about what the page cache is. So the page cache is basically a software cache managed by the operating system. And its main purpose is to buffer file pages in physical memory so that their future accesses to them are faster. In an ideal world, all file pages would be in the page cache so that every access to it is fast. But in reality, you are limited by the amount of your physical memory. Nowadays, all major operating systems, so Linux, Windows, and Mac, implement a page cache. And now that we know what a page cache is, let's look at a simple example how we could exploit it.
Okay, so let's now talk about a simplified page cache attack. Over here, we have a victim, and then on the side, we have an attacker, and we have the operating system kind of in the middle. So what the victim does is it reads a page. The first time you read a page, obviously, it will be a cache miss. So the operating system will go and have to fetch that page from disk, and then any subsequent accesses to that page will be from the page cache. So now that page is in RAM, and now if the attacker accesses that same page, the access time should be very fast because that page is already in RAM. And what we have to do next is now that the attacker has already accessed this page, and the attacker knows that the victim accessed this page because of seeing the fast access time, now we want to evict that page out of the page cache so we can repeat this process and see when the next time the victim brings that same page again. So to do this eviction, we basically access a bunch of other pages that will eventually get rid of the target page that the attacker wants to evict. And so now we have that target page evicted. And again, so if the victim accesses the page again, it will again be fetched from disk, and then it will be stored in cache again. And so this way, the attacker can basically just spy on the victim by just measuring the access times of shared pages.
So now that we know what how an attack could look like, let's look at the first big building block, observing the page cache state. So the first idea is, like in this example, you just measure the access time. But the problem with this is that if you access it, you always load it into the cache, and therefore you destroy the current state of the cache. And this means even if other process or a victim didn't access the page, you still have it in the cache, and because of that you also have to evict it again so that you can monitor future accesses. And that means that your average resolution in time decreases, which is unfortunate. But luckily, the OS developers came to our rescue and have provided nice APIs to do that. So for example, on Linux it's called MinCore, and it basically takes a virtual page range and gives you back the information if this page is buffered in the page cache. On Windows, there is a similar API called Query Working Set AX, and it basically also tells you for a virtual page range information about these pages. So if it's in the working set, how many processes use it, and so on. And with this information, you can also deduce if it's used by multiple working sets or if it's in some working set. And these things are non-destructive, so they don't buffer it, and therefore we get a higher average resolution, because in the case a victim didn't access the page, we don't have to evict it again. And yeah, then we go to the next big building block, the eviction.
Awesome. So the second part of this attack is to reset the page cache to evict the target pages that the attacker wants to observe. And obviously this is necessary because we want to be able to detect multiple accesses to the same page. So we want to get rid of the page so that the next time the victim accesses, you can repeat this process and see precisely when the victim accessed this page again. So this is essentially the bottleneck of the Sidechannel because eviction is slow. And so the ideal strategy depends on the memory management implementation. And there are differences in page replacement policies across different systems. For Linux, you have a global clock pro-like algorithm. But for Windows, you have a different kind of replacement process where you have a per process working set with an aging algorithm.
And as these page replacements algorithms are different, also our approaches are different. And so now let's start with the Linux approach. So in Linux, the basic idea is the same as in our example. We just access new unique pages until the target page is replaced. And therefore our basic eviction set is just a large memory mapped file. And because that's then still quite slow, because the page cache can grow very big, and it basically can grow as long as you have available physical memory, we have developed some optimizations for it. So the first optimization is to add pages to this eviction set which are already in the page cache. So basically we keep the approximation of the current working set active, and that means it is less probable that other pages than the target page are evicted, and that helps us with low eviction times, and the system is more stable because pages that are used are not that likely kicked out. And the second optimization is filling the memory with anonymous dirty pages. And by that, we gain that anonymous dirty pages are basically the last candidates for eviction, And even more so, if you have swapping disabled, they can't be evicted. And therefore, this practically reduces the size of the evictable page cache. And that means we have less possible eviction candidates, and that means we are faster in the eviction. And yeah, with all these optimizations, we get to an average runtime around 149 milliseconds, depending on how the optimizations are configured. You can also get lower, but then you have more CPU utilization and it's not so stealthy anymore. And after seeing these Linux approaches, let's look at the Windows ones.
Okay, so on the Windows side, a page cache eviction basically means the target page is dropped out of all of the working sets. And so the previous approach will be kind of slow. And the optimizations we use for Windows are to increase the working set size and the memory pressure. And this leads to self-eviction of the page, and it's less than 2 seconds. You can also evict page in any other processes. By set process working set size, you can limit the working set size and induce eviction in another process if you want to. And this is for processes with the same integrity level as the attacker. So it won't work with a victim process that's more privileged than the attacker is. And evicting pages in your own working set is done by virtual unlock, which gives around 7.69 microseconds of latency. So, why is this doing this? This is basically not a documented feature.
So let's come to the first example of our side channel. How can you use it? And the first simple thing you can do is just talking over the side channel. So basically chatting over files. And this is done by using a shared file as information carrier. And then you encode the message bits as file page presence in the page cache. So for example, you say the page is present in the page cache, it's a 1. The page is not present, it's a 0. And some pages you have to reserve for transmission control. So you say, yeah, for example, acknowledged or ready to send and such things. And there are quite a few different implementation approaches. And if you have a look on them, we see, for example, that in Linux, if we do it like in the side channel, so with this eviction approach we explained, and use Mincore for observation, we get a speed about around 20.20 kilobytes. And if you use madvice and POSIX-fadvice, which is only possible if the attacker is the sole user of the file, then we can get 81.16 kilobytes a second. And on Windows, we use this process working set eviction with virtual unlock and query working set AX for monitoring the share count. So basically, the attacker and the reader maps it, and if they then see a move in the share count, they know the reader has flushed it from the working set or vice versa. And with this, you can get a speed of around 100.11 kilobytes per second. And all these approaches have in common that they have a very low bit error rate, as long as no other application pressures the system memory. So you can get down to very low numbers here. And the next example we have is an attack on the PHP random number generator.
Awesome. So now let's talk about our second attack, which is the PHP pseudorandom number generator attack. So here the victim process basically seeds their pseudorandom number generator with the system time, and it uses the microtime function, which is used in some frameworks. And the microtime function essentially returns the Unix timestamp in microseconds. And unfortunately, this seeding is used for some cryptographic operations, which is not ideal because it just makes the system weaker because the time is kind of guessable. And what we do here with the page cache attack is we try to detect the use of the microtime call, so we can get exactly when that call was used. So through that, we can infer the system time that was returned by microtime, if we can detect when microtime was called. So this makes the seed recoverable. And what we do is we look for the zip microtime call, which is on page 781 of the executable that is our target. And it depends on different build environment settings. For this particular attack, we use PHP 7.3.5. And the average detection accuracy was within 1 millisecond, which is pretty good. And so the seed was very easily recovered, as we'll now show.
Now let's look at a live demo of this attack. So on the left side, you see the PHP MyFAQ framework, which uses this microtime call to generate the password. And on the right side, you see the attack window. And now what I do is I request a new password. And by doing that, I enter my credentials and then I send it. And then this call to the microtime function is detected by the attack. And then we can basically recover the approximate timestamp which was returned by microtime. And using this information, we can use the same algorithm as the page uses for creating passwords and then create the passwords by ourselves. And as you can see, the ideal password is from the recovered timestamp is not that far away from the real password created by the page. It's around 11 positions away, so that's quite a good result.
All right, so the previous two attacks were really good. Now let's talk about our third attack, which is the UI redressing attacks. So this attack is all about overlaying fake windows on top of real windows to trick the user into typing in sensitive information. So let's see how we can do that. So the first thing we need to do is we need to detect the opening of an interesting window. Authentication windows are a very good example for this. And as soon as this happens, as soon as you detect that the interesting window is opened, you overlay that window with a fake window and trick the user into entering their information there. So this would be like a password that's entered into the fake authentication window. And so how do we detect when this interesting window is open? So we use the Sidechannel, essentially, the page cache Sidechannel, as a trigger. So the attacker detects when that page for the original window, so the real window, is accessed. And as soon as that's accessed, the attacker triggers their own attack and releases their own fake window on top of the real window. And so this provides a very low latency and hardly noticeable attack because it's very fast. You can detect this very quickly and overlay your fake window. And we tested this with a root authentication window on Ubuntu 16.04. And the page in question that the attacker had to detect was page 6 of this library file, essentially. And so we'll show a demo of how this whole process works.
You see that I have the update dialog of Ubuntu 16.04 open. And if I now start an update, a root authentication window spawns, and this is detected by the attack and overlaid by a fake one. And you saw it was a fake window, now below is the real window, and we basically stole the password from the user by this. And you can hardly note this is because the latency is so short. So after we saw all these examples, Trishita, did it have any impact? Was somebody interested in this attack?
Oh, interest. There was so much interest in this. I remember all of the press coverage that we got because of this attack. And actually, that's a good segue. Now, actually, let's talk about the impact that this attack had. So this attack was basically identified as CV 2019-5489, and it generated, as I said, tons of press. And both Linux and Windows deployed a lot of countermeasures to prevent this attack, and there were patches everywhere.
Patches. So let's start with Windows, and what they did is they raised the privilege for querying working set AX on other processes, and that basically means you can't make non-destructive probing of a different working set. And they also did hide the share count for unprivileged users, because with this information you can also indirectly probe if a page is used by a different working set. And therefore, non-destructive probing is no more possible for higher integrity processes. And this basically makes the attack a lot weaker, because you only can attack processes within the same user, which is also interesting, but it's much worse if you attack higher integrity processes like the administrator's process or something like that. And yeah, that it only holds true if query working set AX is the only possible leakage source, which doesn't have to be the case, as we see on the next slide for Linux. And yeah, the eviction in itself is already a lot harder on Windows because of this working set approach they have. And yeah, then let's move on with the Linux countermeasures.
So now let's talk about what people did on the Linux side. So the first thing that they fixed on the Linux side was fixing the mincore system call, which essentially is what was used to spy on these pages in the page cache. So now, after the fixes, mincore only reveals information on writable pages. So this means that if the attacker has only read permissions to a page, it can no longer use mincore to spy on that page because of the patch made to the mincore system call. And so read-only files are excluded, so all of the shared libraries, executables, and basically a lot of stuff that would be of interest to the attacker is now no longer accessible through mincore. And this was merged with the release of the kernel version 5.1.4. And so is non-destructive probing no longer possible? Let's see. Actually, no, because pre-advice 2, which is another system call used with the RWF no-wait flag, leaks the exactly same information that mincore leaked. And so that's not fixed yet. And this basically shows how hard it is to fix an issue like this, because there's a lot of different ways that you can get the same information out as an attacker. So it's like whack-a-mole. So you fix one thing, and then there's this other thing that you also need to fix. So it's not easy to fix a vulnerability like this.
Yes, but the thing is, also, we want performance optimization, so we want to keep them. We don't want to fix all these things that could be abused for attacks, because we might lose performance again. So many of these things we see here, they show sidechannel leakage on the one side, yes, but they're also intended behavior for performance optimizations. So that's really, really difficult to find this trade-off between security and performance. And every optimization that we have, be it in hardware, be it in software, has this potential sidechannel if you optimize something for performance.
So this does not look very good, right? So this means that we won't get rid of side channels because we want to have the performance advantage. And with more and more optimizations that we now add in our software and hardware to keep up the performance and improve the performance year by year, that means we add more and more side channels, and that means we will have more and more leakage. So what we see here is what we asked initially, the microarchitecture in software. There is actually something like a microarchitecture of the operating system. And here we presented attacks on this microarchitecture. And we can expect more attacks on the operating system microarchitecture in the future.
So, conclusion is abstractions eventually lead to side channels. It's an inevitable byproduct of these abstractions.
And we saw that software cache attacks are very similar to hardware cache attacks.
And finding countermeasures is extremely devilishly difficult for these attacks.
With that, we would like to thank you. There were a lot of other people involved with this work, so please check out our paper. And of course, we have to also acknowledge a lot of people that helped us and companies that helped us with funding this research. And with that, we would like to conclude our talk. Thank you for listening. And if you have any questions, we would really like to answer them now in the Q&A, where we are waiting.
Now it's over for real.